Young's double slit experiment. In this video we're going to look at Young's double slit experiment. It's pretty famous, that proves light behaves as a wave. So just first we'll discuss diffraction as a definition. So when looking at waves, diffraction occurs when waves pass through a small opening and they change direction. When we're talking about light, that small gap or the small opening needs to be in the order of magnitude of the wavelength of light. That's why it's very difficult to observe diffraction just in day-to-day life, because the opening needs to be really small. So diffraction occurs in waves and the wavelength remains constant, the speed remains constant, frequency is constant. However, what changes is the amplitude of the wave after it passes the gap. So let's consider a monochromatic light source, meaning all the light that's produced is of that same frequency. Because the way the light's produced, wave fronts may be hitting at different points due to the light source being like a 3D object and the vibration of particles in it. If we put a single slit in front of that source, then that single slit acts as a light source itself now, and the light that's emitted from this one though, it's still monochromatic. However, now it's coherent, meaning there's a constant phase relationship. So from this source, crests and troughs are emitted and they hit this double slit at the same time. So that double slit in front of the single slit acts as two separate light sources that are coherent. The light from source 1 would look like that, and the light from source 2 would look like that. Now, as we have two coherent light sources, at some point in space, we're going to put a screen where the light will fall onto, and interference would occur at these points due to two different light sources being present at the same time. So when a crest is emitted from source 1, a crest is also emitted from source 2, and along this line here we get that constructive interference. At P2 here, the light from S2 has to travel one wavelength further than the light from S1. However, it's exactly one wavelength further, meaning constructive interference still occurs. Then at P1 we've got that half a wavelength difference, so a trough meets a crest and we have destructive interference. So what this does across the screen is produces a pattern, interference pattern of dark spots where the light is cancelled, destructively interfered, or bright spots where constructive interference occurs. So this experiment just proves light behaves as a wave. Now when we're looking at the double slit, focus on this pattern here, the intensity of the light would look like this in real life on a screen. So in this case we're using red laser light, and you can see it's brightest in the middle and slightly duller as the maximums proceed outwards. There's no defined cutoff points between the light and the dark spots. There's no defined cutoff points between the light and the dark fringes. So you can see with this intensity graph, the dark spot is perfectly dark there and the bright is the brightest there. However, in between it's a combination of the two. Now I'll have another video for the derivations. However, we can determine some relationships between the wavelength of light and the fringe pattern produced with the equations on the screen. Okay, so D represents the distance between the slits, and that's in meters. Careful with the conversions in the questions for that. The angle is the angle between the center of the slits and the maximum. M represents the order of the maximum. So if M is 1, it's the first order maximum away from that central one, and lambda is the wavelength of the light. Additionally, if we know the separation between the central maximum and the first order maximum being delta y, we can find the relationship between the wavelength of the light, the distance from the slits to the screen, and also the distance between the two slits. So have a look at the derivation videos for more information on this. Explain why a single slit is used before light reaches the double slits in Young's double slit experiment.